In this lesson, we'll talk about material selection in projects where stiffness is the main constraint. We'll start with a theoretical overview of the approach and then continue with some case studies that will serve as useful examples. Often, when thinking about structural design, people focus a lot on strength, taking stiffness for granted. Having adequate stiffness is essential wherever you want to set a precise limit on deformability, such as in the case of bridges, viaducts, and buildings, to prevent dangerous deformations and oscillations, or in airplanes where the wings and fuselage must remain stable under aerodynamic loads, in machine tools that require precision and the absence of vibrations, or in sports equipment like rackets or golf clubs, which need to be stiff enough to ensure efficiency. Designing with stiffness as a constraint means setting a maximum limit on the deformation caused by a given stress state. Structures subjected to an external force naturally tend to deform. Tension rods tend to elongate, just as beams bend when a moment is applied, and columns compress or buckle under a compressive force. Joints become distorted, and vessels subjected to internal pressure tend to bulge and their walls become thinner. The extent of this deformation then depends on the intensity of the force, the type of stress applied, and on the stiffness of the material. The stiffness of a structure relates a cause, the force, to its direct consequence, the change in shape or displacement. In other words, stiffness represents the resistance that a structure offers to a force that tries to deform it. It's important to clarify that when designing a structure to be sufficiently rigid, the deformations involved are generally quite limited. In particular, they're well below the levels that would cause permanent deformation or failure. The design is done within what's called the elastic range. The strength of a manufactured object depends on both the material and its geometry. The stiffness of a material, on the other hand, is an intrinsic property of the material itself and is defined as the ratio between stress and strain. The quantity that represents this property takes on different names depending on the type of stress. Here, we'll talk about Young's modulus when there is an uniaxial stress, about shear modulus when there is a distortional deformation, and about bulk modulus when there is a hydrostatic pressure related to a change in volume. In all these cases, dimensionally, stiffness of the material is equal to force per unit area, and generally, it is expressed in gigapascals. In many of these projects, the main goal is to reduce weight, and for this reason, stiffness is often considered together with another property, density. And for many materials, there is a precise relationship between these two aspects. In fact, a denser material will have heavier atoms that are more tightly bound to each other, and therefore it will be stiffer. The dashed red line is therefore a sort of close relationship, valid for most families, between stiffness and density. However, some families of synthetic materials try to break out of this kind of valley. To improve stiffness without increasing mass too much, lightweight and strong reinforcements can be introduced, such as carbon fibers. On the other hand, by introducing voids into the material, as happens in expanded materials or foams, you get very lightweight materials, although with a reduction in stiffness. In a design where stiffness is a constraint, the approach to material selection still involves, as a first step, translating the design requirements. Generally, the translation of the design will be structured as shown here. Under the Functions section, the type of load the product will be subjected to will be specified. Under the Constraints section, the main constraint to specify will be stiffness, and then you can add other secondary constraints as needed. Under the Objectives section, you'll specify what you want to maximize or minimize in the project, such as mass, costs, and so on. Finally, the free variables will first concern the choice of materials and, in some cases, where specified, also the possibility of varying the dimensions of the product. It is therefore essential to make these parameters explicit and, in particular, to communicate to the project designer what their scope of action is through the free variables. To better understand the method to be applied, we will present two case studies. These are two deliberately simplified examples. It is important to clarify one point. In these initial phases of material selection, we are not interested in a precise, detailed description of the product, but rather in a simplified model of it. For this reason, even for complex structures, We will refer to classic engineering cases, and so a tie rod will be associated with a tension bar. The handle of a bottle opener will be treated as a bending lever, and the body of a hydraulic piston as a compression column. The first case concerns the choice of materials for the shaft of a golf club. The materials used for golf clubs have changed a lot over time. From the 15th century, when clubs were all made of wood, to today's models that combine metals and composites. There are three main categories of clubs: woods for long shots, irons for mid-range shots, and putters for the short game. From a mechanical point of view, the club must be stiff to transmit energy without deforming, and at the same time be light, so as not to tire out the player. Each part of the club has a specific function and therefore an optimal material. Here we focus on the shaft, where stiffness is the main selection criterion. The shaft of the golf club must be designed primarily for stiffness because it ensures maximum energy transfer to the swing without deforming. This ensures control and precision by preventing the head from changing angle during the shot, and it guarantees repeatability, allowing the player to perform consistent and reliable swings. We therefore propose the project designer translation for the shaft of a golf club. The shaft of a golf club can be compared to a rigid and lightweight lever. Its function is that of a beam subjected to bending. The main constraint is stiffness, meaning it must not deform too much when it comes into contact with the ball. In addition to this, there are secondary constraints. It must be strong enough not to break, tough enough to withstand shocks and impacts, comply with any cost limits, have a standard length, and in this problem, we choose a solid circular cross-section. The characteristic to be optimized is the weight, which should be minimized. The free variables in the design are the choice of material and the size of the cross-section. To sum up, the shaft of a golf club can be compared to the case of a beam with specified stiffness and minimum weight, which can be made from any material with a wide section and as desired. For this combination of design parameters, the material index to use is the square root of E over rho, where E is Young's modulus and rho is the density. This index represents the criterion of excellence for obtaining materials that are sufficiently stiff and lightweight, as discussed in the in-depth lesson on material performance indices. Let's consider the main families of materials and narrow our focus to those with a Young's modulus greater than 20 gigapascals, a strength greater than 200 megapascals, and that are impact resistant. This immediately leads us to exclude certain classes of materials, such as rubbers, foams, and polymers that are too flexible, as well as glasses and ceramics that are too brittle for this type of application. Among the selected families of materials, we'll consider just a few examples. For metals, the most common are steel and titanium. For woods, ash and maple. And for composites, those with glass fibers and those with carbon fibers. Obviously, having a longer list of materials that includes light metals like aluminum, magnesium, or composites with different amounts of fibers would allow for a more precise solution to the problem. In this comparative table of the selected materials, we can see a list of the properties useful for comparison, the elastic modulus, density, cost per kilogram, and two derived properties, the performance index, which is the square root of E over rho, useful for ranking the best materials, and the cost per unit volume, that is, cost per kilogram divided by density, which will help us better compare costs, considering that the rods will have the same length and similar sections. The results are presented here according to the ranking determined by the material index, and the following considerations can be made. Carbon fiber composites are the best solution, but not the most economical. The two types of wood are tied for second place. They're affordable, but less reliable due to the variability of wood and its sensitivity to humidity. Titanium alloys and glass fiber composites are a good second choice. The former are expensive, while the latter are more prone to long-term wear. Steel, despite its excellent mechanical properties, comes last in the ranking for performance because of its high specific weight. However, it could be reconsidered in a design that uses a tubular section. Let's finally take a look at the current state of the art of golf clubs as a sort of documentation phase. The materials currently used for golf club shafts are carbon fiber composites, mainly used in modern clubs, thanks to their balance between lightness and stiffness, which allows for greater swing speed in irons and woods. Then there's steel, used especially in putters to ensure stability and control, but also found in other clubs. Finally, wood, which was widely used in the past, is less common today. For the heads, woods like mulberry or walnut are used, as well as metals such as titanium or aluminum, nickel, and steel, often combined with polymer inserts to dampen vibrations and better balance the weights. For the grip, on the other hand, rubber-based or polymer materials are preferred. Let's now see how the solution would look graphically using a bubble diagram. In the schematic graph, the bubbles represent the different families of materials, while aligned with a slope of 2 serves as a reference to compare the solutions. It shows how composites, and secondly woods, are the materials associated with the best performance, while titanium, fiberglass, and steel are positioned further behind. This type of chart becomes especially useful for quickly identifying the best material at a glance, as well as possible alternatives. We'll wrap up the first part of this lesson here, where we've explained the method behind material selection in stiffness-constrained projects. We've also applied this method to a practical case. We'll do the same in the next lesson, where we'll aim to reinforce this approach by tackling another practical example, this time focusing on optimizing the manufacturing costs.